Okay, we've talked a lot about descriptive stats and how to generate graphs and line charts and calculate statistics. And we're going to move on to probabilities. Because probabilities are incredibly important when we start modeling systems when we have uncertainty. We may know what the outcome could be, but we don't know exactly what the outcome is going to be. For example, flipping a coin, we know we're going to get a heads or a tails, but this next flip, we don't know what it is. Now we can calculate the likelihood, or we can determine the likelihood, but systems where we have uncertainty in our outcome are called stochastic systems. Flipping a coin, the time it takes to do something, and then a probability is the likelihood that a specific event is going to occur in this stochastic system. So what is the likelihood or the probability of flipping a coin and getting a tail? And for that real simple one, it's 0.50, but it can get hard pretty fast. We may have more than two choices, and all those choices may not be equally likely. If we're looking at evaluations, and we may have poor, fair, good, very good, but the distribution of those don't have to be the same. So the probability of receiving a good doesn't have to just be equally likely with the other ones. Think about putting a bike together. This 3 minutes is a little bit aggressive. I don't think that makes sense, but maybe it should have been a probability of assembling a bicycle in 3 hours or less. Well, what do you get when you calculate probabilities? You always have to remember a probability is always a number. It can't be a color. It's not a description. It's not pretty good. It is a number, and it's always a number between 0 and 1. A probability is something like 0.3, 0.92. Those are numbers between 0 and 1. If you calculate a probability of -7 or 1.4, those are not probabilities. They can't be. They have to be a number between 0 and 1. And you can, if you want, you can think of them as percents. That's fine. So a probability of 0.10 is also equivalent to having a 10% chance of something occurring. Probability distributions, when we start talking about all of the possibilities and how do we distribute these probabilities, all of the probabilities for a specific event, all the outcomes, they have to sum to 1. For example, if we stay real simple and talk about shooting a free throw, there's only two choices. And if we say that the probability of making a free throw is 0.7, if that's true, then we know that the probability of missing has to be 0.3 because the total has to equal 1.0. So what does the miss have to be so that the sum of the make and the miss equals 1? So how do we determine these probabilities? One way, and it would be the best way, is to use classical or use equations. There are for some problems, equations, we just plug in some numbers and boom, we've got the answer just like that. And there are some situations where we'll talk about that. For example, when we use the normal distribution, there's someone who's already figured out all of the different probabilities for certain problems, and we just plug in and we get the answer. But I have to admit that doesn't happen very often. So we are going to be limited to the next best thing, and that is either subjective data or data-driven. Subjective is when we don't have a lot of data, we don't have access to it, or we don't know how to use what we have, and we just rely on our experience or our expert opinion. And keep in mind, that could be really good. Just because it's subjective doesn't mean it's not good. We can have people who really understand the system, they just don't know how they come up with it, and it can be a good answer. So don't discount subjective calculations and just people doing it based on their expertise and experience, but I'm not going to teach that. We want to focus on, and it's one of the outcomes of being going through our MBA, is that we want you to be data driven. We want you to be able to take data, turn it into information. So in this case, we want to be able to take data and convert it to likelihoods or probabilities. So we have an example that we're going in the next video. We'll go through how to solve this. But let's say we flip a coin, and a fair coin, so the likelihood of getting a heads or a tails is equal. We're going to flip a coin 20 times in a row. And we're going to count the number of runs that we have. And a run is when we make consecutive heads or consecutive tails. So if I start and the very first flip is a heads, and the next one is a heads, and the next one is a heads, and then the fourth one is a tail, I just had a run of 3. And I want to know what is the probability of getting a run of 4 or more out of 20 flips of a coin. Well, it's a simple problem in terms of easy to explain to someone. It's pretty hard though. How would you go about in doing that? And one way to do it, and this is what we're actually going to do initially, is we're going to run an experiment. We're going to get a coin out and we're going to flip it 20 times in a row and count the maximum run. And if does that exceed 4 or not, then we're going to consider that successful. If it doesn't get to 4, we will not consider that successful. And we're going to run that 20 coin flip experiment a whole bunch of different trials, like 100 different times. And then if out of those 100 trials, and we had 87 of them where we got 4 or more, then our probability, our likelihood of this, we're going to say is 87 divided by 100, or 0.87. So that's what we're going to do. But we're not going to really flip coins. But I'm going to mimic that or simulate that in Excel. So I'm going to show you how to do this in Excel. It's going to be available. You'll have it. Some of the formulas are sophisticated. Don't worry about it. Again, I'm not testing you on it, but I want you to be aware that Excel can be a good predictive modeling tool in addition to just building graphs, and that you can actually use Excel to be a simulation package as well, as a doing spreadsheets. Thank you.